Somewhere over the Arctic this afternoon, the sun is about to go out. Not for long, a couple of minutes at most, but for the first time on mainland Western Europe since 1999.
And here in the studio, it's the middle of a Sydney afternoon, so we're gonna watch it the way most of you will, on a screen, in the small hours, wide-eyed. Welcome to Astronomy Daily. I'm Avery.
And I'm Anna. It's Wednesday, the 12th of August. Today, the only total solar eclipse of the year, and how to catch it wherever you are. A NASA jet that chases the shadow, a magnetic field caught in the act of building a star. Why some worlds cook themselves alive, and tonight, a moonless meteor shower. Let's go. If you only clock one thing in the sky this year, it's happening in the next few hours. Today, the moon's shadow falls across the far north of the planet and gives a lucky, narrow strip of the world a total solar eclipse, the only one of 2026.
Give us the geography because this is a strange one. It doesn't run the usual way.
It doesn't. Most totalities race roughly west to east. This one arcs up and over the pole. It begins at sunrise over the Taimyr Peninsula in Arctic Russia, sweeps across the top of the world and down the eastern side of Greenland, crosses western Iceland, Reykjavík included, then runs out over the North Atlantic, clips a tiny corner of northeastern Portugal, and finishes by crossing northern Spain from Galicia to the Mediterranean, ending near the Balearics right at sunset.
And this is a big deal specifically for Europe.
A huge deal. It's the first total solar eclipse over Western mainland Europe since the 11th of August, 1999. 27 years, almost to the day. For Spain, it's the first since 1905. For Iceland, the first since 1954. People have booked these spots years out.
So if I'm standing in the path, what do I actually get?
Not long, but unforgettable. Maximum totality is about 2 minutes and 18 seconds, out over the Atlantic near the center line. On land, it's shorter. In Reykjavík, totality lands around 1748 Universal Time. That's just before 6 in the evening local and gives you a bit over a minute. Out on the Iceland Snæfellsnes Peninsula, you do better. Then over in northern Spain, totality falls around 1827 to 1833 UT. That's 8:27 to 8:33 in the evening local.
Evening, so the sun's getting low.
Very low. That's the catch in Spain. The sun sits only about 10 degrees up on the north coast and as little as 4 degrees near the Balearic Sea. Gorgeous if you've got a clean horizon, but a hill, a forest, a building, and you miss it. And the weather split is almost poetic. Iceland is climatologically the cloudier bet, Spain the sunnier one, but Spain makes you pay with that low sun.
Okay, now the part most of our audience needs, because most of us are nowhere near that strip. Start with North America, our biggest audience.
North America gets a genuine partial this afternoon. No totality anywhere on the continent, but a real bite out of the sun, and the further northeast you are, the bigger the bite. Eastern Canada does best. Nova Scotia sees around a third of the sun covered, about 33%. Northern Maine gets close to 28%. Montreal about 18%, Boston around 16%, peaking near 1:55 in the afternoon Eastern Time. New York around 9 or 10%, about 1:54 Eastern. Toronto about 8%, Washington, D.C. about 10%, and Alaska gets a lovely one in the morning. Fairbanks around 37%.
And crucially, that's a partial, so the rules are different.
Completely different. And I'll say it plainly. If you're seeing a partial, the sun is never fully covered, so you must keep certified eclipse glasses on the entire time. We'll do the full safety line at the end, but that's the headline for North America. Glasses on, start to finish.
Europe outside the path?
A deep partial low in the evening sky. London around 91% covered, Paris about 92%, Berlin 85%, Vienna 87%. Dramatic, but again, partial, so eye protection throughout.
And then there's us, the Southern Hemisphere, Australia, New Zealand. Be honest with them.
Straight up, we see nothing of this one directly, not a sliver. It's an entirely northern hemisphere event. But, and this is the good news, you can absolutely watch it live. NASA, Time and Date, and the Exploratorium are all streaming from the path, including telescope feeds out of Spain. In Australian Eastern Time, that coverage runs roughly 1:30 to 6 in the morning Thursday, with the totality highlights landing somewhere around 3 to 4:30 a.m. AEST. Set an alarm, make a coffee, and you'll see the corona in real time.
That corona being the whole reason people chase these.
That's it. For those 2 minutes, the moon blocks the blinding disk of the sun and reveals the corona, the faint, pearly outer atmosphere we almost never get to see. It's not just beautiful, it's scientifically precious, which, nice segue, is exactly why NASA is about to chase this shadow in a jet.
So while millions look up, one NASA team is going to look sideways at nearly 50,000 feet. As the eclipse crosses today, a NASA WB-57 high-altitude jet will fly along the path and literally chase the moon's shadow.
Why fly it rather than just stand still like the rest of us?
Because if you move with the shadow, you stretch out your totality. From the ground, you get a couple of minutes. From that jet cruising at around 740 kilometers an hour, the team extends their view of totality to nearly 3. In the nose cone sit 4 cameras, visible and infrared, shooting at least 20 frames a second. The instrument's got a great name, SCIFI, Scientifically Calibrated In-Flight Imagery.
And the science they're after.
The corona's biggest riddles. 1, how the corona gets heated to something like 1,000,000 degrees when the surface below it is a mere 5,500,000. 2, how those great looping prominences form and hang suspended above the sun. And 3, how material in the corona feeds into the solar wind that washes over all of us. The principal investigator is Amir Caspi at the Southwest Research Institute in Boulder, and his line is lovely. The sun is always changing. Every eclipse is different, so we might see something we've never seen before.
And a total eclipse gives them something no spacecraft can, right?
Exactly, and this is the clever bit. Space telescopes block the sun's disk with a little occulting disk called a coronagraph, but that also hides the inner corona closest to the surface, the very region where the heating happens. A real eclipse, with the moon as a perfect occulter, hands you that inner corona for free. Flying above the clouds and most of the water vapor also opens up infrared wavelengths you can't get from the ground. These same cameras flew the 2024 eclipse over North America. The team fixed some overexposed frames and sped up the software, so the 2026 data should come back sharper and faster.
And it's not just the jet. There's a whole balloon army.
There is. The NASA-supported Nationwide Eclipse Ballooning Project, led by Angela de Jardins at Montana State University, is sending students from U.S., Icelandic, and Spanish universities to launch scientific balloons, around 86 of them from Iceland and Spain, before, during, and after the eclipse. They're measuring what happens to the atmosphere when day suddenly turns to dusk. The ozone and the so-called boundary layer near the ground that shifts with temperature and moisture. As NASA's Eclipse Program Manager Kelly Corrick put it, an eclipse gives us a vantage point on the sun we can't get anywhere else in the solar system, and today, students get to grab it.
From the sun's outer atmosphere to the birth of a star entirely, and a 30-year-old mystery just got solved. Using the ALMA array in Chile, astronomers have captured the first direct high-resolution image of a magnetic field wrapped tightly around the jet streaming out of a still-forming star.
Paint the picture. What does it actually look like?
Picture a twisted, funnel-shaped field, a corkscrew of magnetism sheathing the gas that's blasting away from the young star. The target is a mouthful, NGC 1333 IRAS 4A. A young double-star system tucked inside the Perseus molecular cloud, about 960 light-years away. And seeing that field wound around the outflow confirms a prediction theorists have been making for decades about how these jets are launched and shaped.
Why does a baby star even need a jet?
Beautiful question. It's a survival trick. As a star gathers material, it also gathers spin. Too much spin, and it would tear itself apart before it ever finished forming. The magnetic field and the jet act like a release valve. They carry away excess material and angular momentum so the star can keep growing rather than spinning itself to pieces. This image shows the mechanism doing its job.
And there's a bigger echo here, isn't there?
There is, and this is the part I love. The same basic physics, a magnetic field channeling a jet, is thought to play out at wildly different scales across the universe, from a newborn star like this one all the way up to supermassive black holes that fire jets across entire galaxies. Same trick, unimaginably different sizes. The work is led by Ching, a former Jansky Fellow at the U.S. National Radio Observatory, published in Nature Communications. And a small point of pride for our part of the sky, ALMA sits high in the Atacama in Chile, very much a southern hemisphere machine.
Here's a question that sounds simple and absolutely isn't. Why did Venus, Earth's twin in size, turn into a furnace while Earth stayed livable? A planetary scientist at UC Riverside, Stephen Kane, thinks a big part of the answer might be something we routinely overlook: how fast a planet spins.
Spin? Really? Why would rotation decide whether a world is hospitable?
Because rotation sets how a star's heat gets spread around a planet. It shapes the winds, the weather, the way an atmosphere and any oceans circulate. Earth's roughly 24-hour day keeps the energy moving and the climate regulated. Spin a world down slow enough, Kane argues, and you may tip it toward a runaway greenhouse. Heat pours in, can't escape, and you end up with Venus, a crushing atmosphere and a surface hot enough to melt lead.
So to test that on other planets, we just measure how fast they spin?
That's the rub. It's genuinely hard. In a paper accepted by the Astronomical Journal, Kane warns that when you look at a distant planet, the motion you detect might be its howling winds, not the solid body underneath. Exactly the confusion Venus throws at us. The proposed fix is to observe at several wavelengths that probe different depths of the atmosphere and separate the true spin from the wind.
And there's a mission coming that could actually run this experiment at scale.
There is. ESA's Plato, due to launch in March 2027. It's built to find and monitor lots of planets, and Kane reckons it could turn up hundreds of Venus-like worlds. If they're all slow rotators, that's a strong hint that spin really is a switch between a living world and a hellish one. If they're all over the place, we look elsewhere. Either way, a lovely, testable idea.
And the sky isn't done with us today. Tonight, the night of the 12th into the 13th, the Perseid meteor shower hits its peak. And here's the gift. It's genuinely moonless because the same new moon that's giving the north its eclipse leaves our meteor sky pitch dark. These are the best Perseid conditions in years.
Best window?
Between midnight and dawn, and best of all in the pre-dawn hours of the 13th, when the radiant up in Perseus climbs highest. For the Northern Hemisphere, North America especially, this is your night. Get away from town lights, look up after midnight, give your eyes 20 minutes, and let them wander. No telescope, no glasses, just a dark sky and patience.
And for those of us down south, where Perseus barely gets off the floor.
For Cygni and the Southern Hemisphere, the Perseus radiant only just scrapes the northern horizon, so you'll catch a trickle at best. Don't fret, the evening sky pays you back. Right after sunset, Venus is blazing low in the west, magnitude -4.4, impossible to miss, and just past its half-lit dichotomy phase if you've a telescope. Then before dawn, there's a fine lineup of planets strung across the eastern sky. And Comet 10P Tempel 2 is still a southern hemisphere favored binocular target, one for our part of the world.
And the eclipse times, one more time for everyone?
For North America, it's an afternoon partial, Boston peaking about 1:55, New York about 1:54 Eastern Time, glasses on throughout. For Australia and the wider southern hemisphere, it's the live streams, roughly 1:30 to 6 in the morning AEST Thursday, with totality around 3 to 4:30 a.m. Thursday. And that brings us to the line we never cut. Never look at a partly eclipsed sun without proper protection. Use eclipse glasses or a handheld solar viewer that meet the ISO 12312-2 standard. Ordinary sunglasses are not safe, and neither is an unfiltered camera, phone, binocular, or telescope. If you're in the path of totality, you may look with the naked eye only during those brief seconds when the sun is completely covered, and glasses go straight back on the instant the bright edge returns. Not in the path, then it's a partial the whole time. Protection stays on from start to finish.
Whatever you catch today, a partial, a stream, or the meters tonight, tell us about it. Everything lives at astronomydaily.io. The back catalog, the daily news feed, the newsletter, and a spot to leave a review or drop us a line. We're at Astro Daily Pod everywhere.
We'll be back tomorrow to tell you how Shadow Day went, the images, the science, and whatever the sun decided to show us. Until then, from Avery
and from Anna, enjoy the eclipse, mind your eyes, and
clear skies.
Astronomy.